So we have a Klein-Gordon equation, dA or dA squared plus m squared times phi equals 0, but now we want to create these disturbances in the field. So we want a special solution. We call this phi 1. We're going to have a one disturbance at some location in space-time, and of course, therefore, this becomes a delta function, right? It's a localized point source disturbance. So in space-time, so we have xa minus xa prime, say, where xa is just a 4 vector. So this has, well, depending on the coordinates we want, it's time, x, say, x, y, and z. But let's make life easier for us. So this is the kind of thing we have to solve. Let's assume t independence in the disturbance, and let's go to a 1D universe. So we have a one-dimensional field, and these disturbances can travel left and right. And so our equation now becomes minus 2 derivatives in x plus m squared times phi 1 is equal to delta. And now we're just going to say position x minus x prime, so the disturbance is at x prime. And, well, actually, let's change this. xa naught, maybe that's better notation, delta x minus x naught. So here's the x-axis, here's x naught. That's what disturbance is. It's going to propagate away from there, and we're going to see what the solution is, what the field is like, how the field changes at values of x given the disturbance at x naught. We know what this looks like when this is equal to 0. It's just these plane wave solutions. So we're going to have plane wave solutions now that have an origin at x naught. The disturbance is here, and they're going to travel left and right. So it's not surprising that phi 1 is really just a sum, or in this case an integral, because we're in the continuum of plane wave solutions. E to the minus I k x minus x prime. Right? Disturbance is created at x prime, and it's weighted by some function of k such that k obeys our standard relation, right? K squared minus m squared equals 0. And so that's the thing that we have to solve, and ka is our 4 vector. In this case, it's a 2 vector, so it looks like that. It's frequency and wave number. So what's the solution? Well, let's notice that there's an issue here. You know, where our solution is valid, this thing goes to 0. So it's not surprising. Well, let's say that we ask a mathematician to give us a solution, but we should expect to get something that is strong near here and dies off as we move away. And in fact, phi 1 ends up being a decaying exponential function with the m term in it, where the distance, sorry, I had x naught here, and I again wrote x prime, so this is x minus x naught. 4 pi x minus x naught. So it looks like that. So the effect of the field at x due to the disturbance at x naught has these features, where we can see that the disturbance is large for x approaching x naught, is small for x minus x naught in either direction, right? This way or that way, so the absolute value as this goes to infinity. And importantly, the disturbance is larger at x for smaller m. So you make a disturbance, and it can have a greater influence further away if the m parameter is smaller, and vice versa. If the parameter is larger, you'll have a weaker effect further away.